we have some manifold n. It's a Riemannian manifold, it has magic. You can always imagine it if you use just a domain in Rn with some metric tensor or more sophisticated surfaces in triangles and with a boundary. On this manifold we have a Riemannian Laplacian, which just a fixed notation we assume to be Neumann, have a Neumann boundary condition. Then we have the eigenvalues, lambda k, and the corresponding orthonormalized eigenfunctions phi k. And our data is a boundary, so the whole boundary again. And also lambda k and the values of the eigenfunctions on the boundary. Now, we look for the initial boundary value problem. We look for initial boundary value problem. We construct a Weber equation related to this Laplacian delta. We put the Neumann boundary source f on the boundary that starts somewhere above time t equal to 0, and we assume that before time t equal to 0 there was complete rest. Then we have solution that we know UF. I typically call it wave because it's corresponds to the acoustic wave. And then if you expand the solution u in the eigenfunction with respect to phi k, so u at the time t is uk at the time t by phi k of x sum. Then the corresponding Fourier coefficient, I still love, let's say eigenfunction expansion coefficient, but I would prefer to say Fourier, Fourier is short, has a very precise formula in terms of the values on the boundary of the eigenfunctions, eigenvalues, and the source f. So that's called logarithmic formula. That was the first pillar of the boundary control method. And the second pillar was that if you start taking f that has support not on the whole boundary but on the piece of the boundary gamma, 0t, so it works from 0 to t and on the piece of gamma, and you take all possible f from c0 infinity and look for the corresponding waves at the time t, then the closure of this space in L to n gives you all L2 functions in the domain of influence at the time t. So this is domain of influence. I sometimes will be writing instead of n. Please interrupt me. N here is always m. Remaining manifold is f. So this is all the points inside n that lies at the distance less than t from this chosen gamma. So these are two pillars, and now we build up a theory based on these two pillars. The first thing is the following. Let me recall that this eigenfunction transformation, Fourier, generalized Fourier, that makes from the function a of x its Fourier coefficients, right? So that a of x is sum ak phi k of x. This is a unitary transformation. It's from unitary transformation from L2 of n to L2 small. It's a unitary transformation. Now, therefore, it transfers any closed subspace in L2 of n in L2 small. So let us denote by L2 small of gamma and t, that is Fourier transform of L2 with supports in n gamma t. Okay, so this is Fourier transform of this space. Then our first observation, which is actually the crucial one, very simple, is the following. Given boundary spectral data is lambda k and phi k in the boundary, we can find L2 gamma t for any gamma on the end and t more than 0. So boundary spectral data determine this class of the subspaces of L2 small. So this lies in L2 small. Why is that? Well, we take arbitrary f from C0 infinity gamma 0 t. We find its Fourier coefficients using Bloch-Averichinski formula. We get a subspace when we write f, and then we close it. And then because of Sartar's result, approximate controllability, when we close, we get the closed subspace. This is exactly the Fourier transform of functions is supporting n gamma t. Okay? Now, what you can extract from it? Somehow, what we have, look, we have somewhere behind the wall that we don't see. All these subspaces, subdomains n gamma t, they're behind the wall, we don't know that. But we have here, we can construct these subspaces L2 gamma t. They are now disposed. So, for example, let's look for the simple properties of this L2 gamma t. First property. If T plus is more than T minus, then L2 gamma T plus is larger than, okay, that's all, is larger than L2 gamma T minus. Yeah? Because if you look for the domains of influence, what happens? So this is n gamma T minus, and this is n gamma T plus, right? It grows. Because the wave goes further. So this subdomains grow. You see it in the Fourier side. So by that Fourier side, I will call what goes in L2 small space. The second thing, if T is large enough, then L2 gamma T is the whole L2. Why is that? We agreed, we didn't agree, but actually I imposed the condition that our manifold is compact. Therefore, if time is more than the diameter of the manifold, you cover the whole, this n gamma t for sufficient large t, namely t more than diameter, will be the whole manifold. So n gamma t will be n, and therefore L2 gamma t will be the whole, L2 gamma t will be the whole L2, and the signature will be the whole L2 small. Then the second story. For the same case, for case A, case 1, L2 gamma t plus minus, this is subspace and this is small subspace, as we know. So if you take this larger subspace, subtract the smaller subspace, take the orthogonal complement, this will be Fourier transform of the following domain. It's L2 of n gamma t plus minus n gamma t minus. Agree? So this t plus corresponds to this subspace, t minus to the smaller one, and this, when we subtract it, will be this layer, this slice. Property 4. You just, what do we do? We look at this domain, this manifold, see what happens there, and then translate in the Fourier image. L2 of n gamma 1 P1 plus L2 of n gamma 2 T2 will be Fourier transform of the union, oh sorry, let's write a little bit. It's gamma 1 T1, and this is gamma 2 T2. And this is Fourier transform of the union n gamma 1 T1 union n gamma 2 T2. So this is just if you wish, the linear scalar to these two subspaces. They're not orthogonal, it's not even direct product. But anyway, you have this one, you can find the linear combination, and that will be exactly the Fourier image of the union. So maybe a picture here is important. So let me draw a picture here. I take a very big N. Say this is gamma 1. And this corresponds to T1 minus. This corresponds to T1 plus. And this is gamma 2. And that corresponds to T2. I say it's T1. So therefore, when you get the union, that will be, say this one, it will be this domain. Yeah? So you will find out what is the Fourier image of the union of these domains. Okay? So you don't see the domains, but you see what happens in the Fourier image. And now using this thing, we construct a very important object. I even have a name. Boundary distance representation, and it is called R of n, of Ng. What is this creature? So what we did is actually preparatory to build this R of n. This is the following creature. You have a manifold, this one. Actually, you don't have it. It's God that have it. You have only something in the boundary. But there is a manifold, and if you take any point x inside, you can construct the following function. R is associates to the point x the function Rx of z when z runs over the boundary. So to each point inside, we affiliate a function on the boundary, and it's a very simple function. It's just the distance from this given x to z. So this is fixed, given, take fixed, and this guy varies along the end. So we are staying here and measuring, well, you don't can do it, but I mean somebody who is behind the wall is staying here and measuring the distance from x to various point to the boundary. So they have a map, R, that maps from M, sorry, it's M, to R of n. And this is actually a Lipschitz function, because the distance function is a Lipschitz function. So it actually lies in continuous function on the boundary, and sometimes it's useful to imagine it as a L infinity function on the boundary. So for any point, you associate a continuous function on the boundary, which actually is Lipschitz, but at the moment we don't use it. Okay? So now we want to build this R of n. Now let me say that this is a very, very, well, it's the question, of course, for this reason, it's quite old, but for the development of differential geometry, rather, not a particular old idea. The idea is that you represent a manifold as a class of functions. The first, as far as I know, the first person who used this idea, the first actually two people. So once again, you look for the manifold, for example, a Riemannian manifold, and you try to analyze its property by looking for the properties of something embedded in the class of the functions. So the first paper was actually, the first who did it was Kratowski, Wojciechowski. Well, and what they did, they started a Riemannian manifold and they associate to any point x, so to any x, they associate the function on the manifold. That's called dx of y. So this x belongs to n, and y also belongs to n. And this is just the distance from x to y, okay, from y to x. Okay, so seems very, very trivial, but it turns out that it's a very important tool that recently become more and more important. You see, here we try to do something else, something similar, sorry. The only point that we associate to the point a function on the boundary, not function on the whole manifold. And as I say, in recent years it become very, very strongly developed idea. There is a relatively new area of differential geometry called geometric conversion. That's very related to inverse problems, actually. And basically made by Gromov and Foucault. And they use, Foucault especially, embedding of the manifold in different classes of functions. So that's a bridge from geometry to analysis, right? These study functions.
So what can they get out of that?
The properties of the, when the corresponding class is pre-compact, and what are the properties of the limit? What Foucault did, he said that some particular class of Riemannian manifold is pre-compact in Gromov-Hausdorff topology, and the limit has this and this properties. Okay?
So looking at families of Riemannian manifolds.
Yes.
So one Riemannian manifold corresponds to families of functions.
Yes.
And then I see.
And these families are families. Okay, so that's the only point how to construct this. This R, as I say, is called boundary distance representation. So we have that, and we want to do this. We want to construct actually R of n. And we do the following trick. Let us divide the whole boundary, divide gamma, divide the n into, not intersect, of course we intersect by measure 0. So it's gamma 1, so it's gamma 2, and let's say gamma 3 into union of gamma j from 1 to some j capital, and diameter of each j, of each gamma j is less than some chosen delta. You divide in small p vowels, you divide into grid if you wish. Now, as I said, when time is large enough, namely when t is more than diameter of the manifold, this L2 will be the L2 gamma t for any gamma will be the whole L2 small. So what you do, you divide the interval from 0 to this diameter by delta steps. So 2. Let k start from 1 to diameter divided by delta. We chose this delta. Well, you say, well, it can be not integer. Okay, make it the next one integer. And now let's do the following trick. Let the k will be the vector. Somehow probes. K will be the vector k1, k, j. J is the number of these boundary pieces, and each k, j runs from 1. Let's call it k capital. It's no more the double column. It's just this number. Obviously, j capital and k capital depend upon delta. The smaller delta, the more j and k. So we have delta, and we have this k, and we associate the following object. I called it it's n k. I wouldn't write delta specifically. So what is this? This is intersection from j equal to 1 to j capital of n of gamma j k delta minus n of gamma j k minus 1 delta. Well, that means it's an important thing, so let me write it more carefully. In big letters, n of k is intersection over j of n of gamma j k j delta minus n of gamma j k j minus 1 delta. What is this creature? Well, you look at one this thing. This thing corresponds to the layer, right? So if this is gamma 1, then this creature will be this layer. Obviously, layer is thin. Its thickness is delta. So this is K1 minus K minus 1 delta, and this is K delta, K1 delta. Then take another, say for example this one, and well, let me probably put it here, gamma. That put it gamma 2 not here, but here, gamma 2. So that will be something like that. So this will be K2 minus 1 delta, and this will be K2 delta. So these are two layers. Now let me take the third one and stop, otherwise it will be long and delta is small. Let me put this one, gamma 3. Let's say two possibilities. For example, this one. Oh, I can use different colors. Wow, that's great. So this is small k, K3. So this is K3, and say this is, for example, K3, another K3, right? It's K3 and K3 prime, right? So, and then what we do here, we take intersection, we choose K, takes intersection of all respect to all J. So now it's only 3 of them. So if I take, for example, this K1, this K2, and this K3, what will be the intersection? Empty, right? But if I take this K1, this K2, and this K3, the intersection will be this small piece. Yeah? Now we don't see this picture because it's behind the wall. But what we can see, we know that if we make Fourier transform, so that's LK. So let us look for the Fourier transform of this MK. I think for the Fourier transform of this, by the way, it's called slicing procedure. We slice our domains this way and this way and this way and that way, and many things are zero, but still all together give us the whole manifold. Right? So this is f of nk of L2 of nk is the following. What we do, we either intersect or take the set minus. Aha, when we take the set minus, we get that. So f of the set minus is the orthogonal difference. And when we intersect, and I didn't call it, when we intersect, we just get intersection. Did I got it here? No, it's probably property 5 that I need to write down and about it. So if you take 5 L2 gamma 1 T1 and intersect with L2 gamma 2 T2, that will be Fourier transform of L2 over intersection. And gamma 1 T1 intersection and gamma 2 T2. Okay? So therefore, in the Fourier side, if we translate our splicing procedure into the Fourier side, we do the following. We have intersection this intersection corresponds to intersection here, from j equal to 1 to j capital. And in the brackets what they have Fourier transform of this set minus. And set minus is this one. So it is L2 gamma j kj delta minus L2 gamma j kj minus 1 delta. And from boundary spectral data we can construct it. Now I won't say the procedure is very easy, but in principle you can construct it, right? So you would know all these things for all division in the gamma, into gamma j's and all kj's. So you take me down, give me delta, I cut off my boundary into pieces of the size not more than delta, I slice my manifold by these slices, and I construct this thing. Now, it is not particularly difficult to see, and we see it actually later, that let's put it like a note, and I will return to it later. I will actually, it follows from some construction that I'm going to explain. Note that when delta tends to 0, the size of this intersection, as we see, goes to 0, right? Then diameter of nk tends to 0. The call it's less than some epsilon depending upon the delta, and the epsilon of delta tends to 0. So it's uniformly bounded, and the size goes to 0 uniformly. Okay? So we do a hell lot of job by cutting and looking for these subspaces. What can we do with that? Okay. By now I can delete that, by the way. We already used what we need. Let us think. If our nk was empty, homogeneous has measure 0, what will be this space L2nk? If the measure of nk is 0. So we're looking for the functions from L2 that have support in nk, and nk has measure 0. What are the functions? What are the only possible functions? 0, right? So therefore, in the Fourier side, the corresponding this subspace, I also called, by the way, I called it L and K, if you mind. Then, so there are two possibilities. If measure, or let's say volume, because I think I use volume, right, for Riemannian volume. If volume of nk is 0, this is equivalent to the fact that L2 nk consists of only 0. Now, the whole subspace just degenerates to 0. The second possibility, if volume nk is strictly more than 0, and by the way, we can make that nk is an open set, then this is equivalent to the fact that L2 nk is infinite dimensional subspace in L2 small. Right? It has some ball or some small radius, and you can build up infinitely many linear dependent functions there. Right? There's a big difference. Either 0 or infinite dimensional space. So what we do next, we arithmetic. So we constructed all this L and K.
I'm losing you at something. So if I remember, your beginning data was that you had the eigenfunctions on the boundary and this.
And eigenvalues.
And then so I've lost track of, like, from that, what can you construct here?
From that, if
you can just review that.
From that, you can construct these spaces.
Okay.
So this is the dominant influence of gamma at the time t, and this is its Fourier transform.
So you know all these functions.
You know, well, you don't know function, you know their Fourier coefficients. You know Fourier coefficients of the waves that produced by the slice gamma 0t, for any gamma and t. There's a logarithmic formula plus the time.
But I know all these Fourier coefficients, but can I associate one particular set of Fourier coefficients with something, or I just have this class of functions, that's it?
You have, when you write gamma and t, you have a family
of t varies. Okay.
T varies and gamma varies, right? So you have a family of these subspaces, okay? So it is beyond disposal because the Bulgarisky formula and then you close. And then I deleted here what we can do. We can take the unions of two domains of that type. We can take intersection of two domains of this type. We can take the subset gamma t1 minus gamma t2. That's what we do here. So look here. Here we take Z minus, and that corresponds to L2 orthogonal minus of L2 of this one. And then we intersect, and that corresponds to intersection. So that's how we can do it.
Okay.
And what is this thing? This is, you divide the boundary into small pieces, and you divide the time from 0 to diameter by delta. So you come to this k. And then you choose a vector k, k1, kj, and you build this option. And behind the wall, where people see the manifold to this option correspond the intersection of these layers. In the majority of cases, as we see from the picture, it will be either empty or have measure 0. But still, altogether, they cover the whole space, correct? So, therefore, now we have that. It's in our disposal, and then we distinguish between two things. If this subspace is 0, this exactly means that the intersection of the layers is either empty or have measure 0. Okay? But because there are only a lot of them, but still finite number, and therefore the union of those guys that have measure 0 is measure 0. Okay? That means that if you take any ball from there in any vicinity, it will be the point outside of this measure 0. But if the intersection has non-zero measure, and then you can see that it contains some ball, small ball, then this intersection will be a proper subspace of infinite dimension. So then you do the following trick. Well, basically, you throw away everything that is 0. And to each, so if L2 and K is not equal to 0, we build L infinity function. R and K of Z. Remember, Z belongs to the bound. What is this function? Well, it's very simple. This will be equal to Kj delta if Z belongs to gamma. If you look at the picture, what does correspond? So we look at this intersection, and this is gamma 2. So in gamma 2, we take this K2 delta. So in gamma 2, the value of this function will be K2 delta. In gamma 1, this will be K1 delta. Okay? So altogether, because the union of gamma j's is the whole boundary, we have an L infinity function. By the way, this function is bounded by diameters, from 0 to diameter. So what? Now we come to the fold. Now now the critical point is that all these things are small. So if if this set is, if this subspace is not zero, that means that this intersection is not empty. There's a point there, right? Let x belongs to nk. So any point here. Then if you look for the distance from the point x to z, and this z belongs to gamma j, what can we say about this distance? What can we say about the distance from any point here to gamma 2? Sorry? It's between k2 minus 1 and k2, correct? By delta. And therefore, because gamma 2 is small itself, you know, it has diameter d, we get that the distance from x to z well, will be dx to z when z belongs to gamma j will be more than kj minus 1 delta and less than kj delta, and then, well, if you, for example, take this point, so you can, and the nearest point will be here, so that's plus delta. That's how long you can go along the boundary. Agree? Okay. So that is in when z goes to zj, and if you look for the responding function r and k, its value will be kj delta. And therefore, if you look for r and k of z minus d of xz, when z belongs to zj, z goes to gamma j, we subtract from here kj delta. So this will be less than delta. Right? But now we can forget this gamma j for any j. So that is what you have. In other words, that means that if you look for L infinity distance, well, okay. So therefore, that if z lies in this intersection, you have this inequality. Now, let me recall what was Rx of z. Rx of z was exactly d from x that is fixed to variable z. So I can put here Rx. Let me delete and put Rx. But now, almost all x lies in some of these non-empty intersections. Those that don't lie in non-empty intersection, they lie on the measure 0, and therefore, in any small vicinity of them, there is a point from one. Say, if you take the point, for example, here, well, then it will be you move at any small, and you get into here. So, what does it mean? What does it mean? How can you say? Basically, that means the following: for any x, there is nk with this property. Agree? Because any x, like I will forget about this measure 0, lie in some of these sliced objects. And moreover, for any nk that is miscible, that means that this L2 nk is not 0, there is a point, because that's how we choose it. Right? There is a point x with this difference. Mathematically, that says the following. So what we get is the following result. We have shown, we've got that the Hausdorff distance in L infinity between R of n and R of k is less than delta. So R and K is just the set of R and K of Z if L2 of nk is non-zero. That basically means the following. You take any distance functions and there will be, and the corresponding x will lie in some intersection set, right? And if you take any intersection set, there is a point x with this property. Okay? Nothing more. But we can do this. We can actually do it in finite number of steps. Not finite, it's infinite. What do we do next? Well, our actual goal is, it's n. I beg your pardon. M is n. Our actual goal is R of n. So what we do? We make delta tend into 0. Then there are more and more functions here, and in the limit that gives us R of n. It's called inductive limit, but you imagine, right? Because there's a better and better piecewise continuous approximation of the distance functions.
So you're basically trying to construct a distance from any point in the interior to a point in the boundary.
Exactly. Though I don't know points.
Sorry?
I don't know points.
You don't know points?
They're behind the wall. I know only functions. I only know distances from something that corresponds to the points to the boundary.
So, okay, but I see.
You see?
So one thing is, so you're saying that the point Z that you're saying, so you're going to actually target one of those small things. Right?
Yes.
So, and you're doing these layers and layers, right?
Yes.
So you have to take enough layers so that it gets it into a small thing, right? Because it depends on dimension there in some sense, right?
Of course. You know, the more dimension, the more slicing things. It's exponential. It's like, well, it's exponentially growing because you have thin layers. You divide into diameter delta the boundary, and boundary has dimension n minus one, right? So it's quite exponentially growing object when delta goes to 0. But at any step is fine. Okay? So therefore, you see, you get a larger and larger set of piecewise constant functions, which ones when delta goes, and in the limit they give you L to n. Lim when delta goes to 0, R, and K. I skip here, but you see that of course this MK depends also upon delta, right? Gives us R of n. Okay? Now again, this is just set of the function of the boundary. We know that they're corresponding to the distances from the point inside the manifold to the boundary. But we have no idea, what you give me a function from here, what will be the point? I even don't know what is n, by the way. I know on the boundary. It's actually a representation of the manifold in the class of function. As I say, that goes back to Kartovsky-Wojciechowski. By the way, you probably know about Zorn lemma. Yes? Zorn choice, axiom of choice, right? It's actually Kartovsky Zorn lemma. Kartovsky proved it 2 years before Zorn. But Zorn was German and Kartovsky just Polish. Okay, so now they have this R of n, and forget how less. Now we work with R of n. They already build it. What they can do out of it? I believe this picture. Can I do it? Rakesh asked me how we find topology, differential geometry, and then Riemannian geometry. So we do the following. So now we have R of n. This is a set of functions in L infinity, or let's say I simply with C on the n, and of course it's L infinity. Yeah.
So Rn is in relation to the distance functions, right, from points to boundary. That's what Rn is?
Yes. So this is a set of all boundary distance functions. So Rx of z, that is dxz. So z belongs to the boundary, right? The only point that you don't know the corresponding x. You know just R of z. All possible R of z. Okay? Now, look, this is a set lying in L infinity. And L infinity, of course, is a Banach space. So therefore, we can introduce the distance on the set R of n, just looking for the distance of the function L infinity. So d infinity between R1 and R2, the R1, Ri of z belongs to R of n, is very natural, just the usual L infinity norm. That, of course, we can do. It's C norm, but C is an infinity norm. The point is that when you try to do it numerically, we didn't do it numerically, but you see from approximation, if you stop at some delta, you get not continuous function, but these small jumps. So that's the natural distance on this R of n. And we have set with a distance. By the way, with respect to this distance, it's a complex set. It's easy to see because it's closed. So then, because actually any R corresponds to x, when R converges, then x is converges. So it's complex set with respect to this distance. So the first story is the following. Our first step is to recover topology of n.
So you got the metric.
And now first topology. First will be topology, just pure topology. The second will be differential structure, the third will be metric. And the same will be in Lorentzian case.
No, so not the metric one. It's a metric space, the metric in the sense of the metric space.
No, not in this case. No. I'll answer in more detail as your question.
Okay.
No, it's pure topology. What is open set, what is closed set. So, and for this sense, we prove the following lemma. And they even proved it during the last 10 minutes. Rn with this symmetric space is homeomorphic. This is homeomorphic to n with its Riemannian. This is Riemannian distance. They are not equal. I even show that this is not that. But they are homeomorphic. So I recall you, we have this map R from N to C. I put it to Rn. Then we are automatically onto. So that means that X by R goes to the distance to Rx of Z. That is distance from X to Z. Let me recall you, sorry, of course you know, but better recall. You won't kill me at all. The following simple result from topology is the following lemma. Let X and Y be Hausdorff spaces. spaces of Matthew-Hausdorff. Let phi from x to y be first bijective. 2, continuous. Then phi minus 1 from y to x is continuous, i.e. phi is homomorphic.
Need compactness?
All right, yes, I need that x is and x is compact, right? Okay, so in our case, f is r. F is r. X is L to n. Sorry, x is n, and y is Rn. So we need to check that for x equal to n, y equal to Rn, and f equal to r, these properties are satisfied. Well, bijective means injective and and surjective. It's obviously surjective because that's the definition of R of n. Yes, that's exactly the image of n. It is also continuous. Why it is continuous? Well, because if you look 2 points and you look for the Rx minus Ry in L infinity, that will be supremum, actually maximum. But okay, let's put supremum. Rx of z minus Ry of z. Yeah? But this is distances. So this is just distance between x to z and x to y, and y to z, right? But we have triangle inequality. This guy is less than the xy by triangle inequality. So,
sorry, what is f here?
This is an abstract plan. F is phi. F is phi. Okay. So, so using this lemma, we see that our R is a homomorphism between this space that we constructed and ND. So that means that we find the homomorphic ND as a homomorphic class. We find the topology of ND. How many holes, what is the, what are Betti numbers, if you like, about Betti numbers, and so on and so forth. Okay? By the way, you remember I told you that when your delta goes to 0, then the size of each intersectional slices goes to 0. That's actually follows from this thing, right? Because okay, sorry. No. Well, what we need also to prove, that is simple part. We need to prove also this guy is injective, right? So we need to prove. It remains to prove injectivity. Assume the contrary. Assume that there are two points x and y, x, y, such that Rx of z equal to Ry of z for any z belonging to the bound. Okay, so these are remember these are continuous functions, so they have minimum. Let's take the point z0. Z0 is arc minimum of Rx of z and Ry of z. Because they're the same, arc minimum is achieved at the same point z0. So arc minimum is the point where minimum is achieved. If there are several of them, take any. So this is x and this is y. Because this is the point z0, R of x 0 is less than r of x for any z, remember this is distance, that means that the point z0 is the closest point to x on the boundary. Agree? So let us look for the shortest curve from z0 to x. And we know that shortest curve is a geodesic. Say, in the equivalent case, it's just straight line, right? So this is a geodesic that comes from z0 to x. Moreover, this geodesic should be perpendicular orthogonal to the boundary. Again, it's sort of, I mean, the point is, locally, Riemann geometry is just using equivalent geometry. Assume it's like that. Assume it goes this way. So this is not pi over 2. But then you can say, well, because we all know that hypotenuse is more than cathets, that this will be the closer point, right? If you go this way and then go this way, this point will be closer to x than z0. But that's our definition of z0, that is the closest point. Okay? So therefore, x lies on the normal geodesic from the boundary, from the point z0. At the distance, it's called r planes, but this is distance. At the distance rx of z0. Correct? So you shoot a normal geodesic, go along that during the time rx of z0, and you get to x0, to x. What about y? That's the same. Because the same geodesic from the same point and also normal, and the distance is the same because we have that. So you shoot the same geodesic to the same direction, and therefore x equal to y. Okay? So if r of x equal to r of y, then x equal to y. Let me please repeat. If r of x equal to r of y for any z, it actually means that the point where they both achieve minimum is the same as z0. This point z0 is the closest point on the boundary both to x and y. Okay? What's the question? What does mean? So this is the closest point on the boundary to x. It's the closest point. You look for the shortest curve, shortest path. It will be geodesic. Moreover, this will be normal geodesic, because otherwise you make a shortcut, right? If this is your boundary, this is this one, this will be definitely closed. So it is a normal geodesic. We start the point z0 and need to go the distance rx of z0. What about y? It's the same z0, the same normal geodesic. You go the same distance ry of z0, but they're the same. Well, come on, you'll come to the same point, right? So x equals y.
The normal geodesic is unique.
Yes, well, in C infinity case, right? Yes. Geodesic is defined by the system of ODEs, right? So system of ODEs of, well.
Okay, but the normal geodesic has a unique starting direction. That's right.
Yes, normal is unique, right? So therefore, x equal to y. And the proven GT. So today we recovered with you the topology of N. You still need to recover differential structure and the metric test. I will do it tomorrow.